Thank you, Elizabeth. Well, that's the first time ever, and probably the last time ever, I'll be described as a rock star, so there we go. We'll take that one. Now, interestingly, when I first proposed this topic for this lecture, I don't think there was any papers that I could find in any offshore conferences that talked about pile runs. So I thought it was a great topic, and but then I've counted up that I think there's at least 6 papers in this conference that have got pile run in the name, and but there's only one that's got pile freefall in the name, so this one's unique. But of course, pile freefall is the same as pile run, so we've just called it pile freefall in Australia, and everybody else is calling it pile run, but it's basically the same thing. So hopefully, some of you will have seen, I did a couple of SUT seminars over the last 2 years, I think one in the US and one from Perth. So I think I know some of you, quite a few of you perhaps have seen them. There's a little bit of background going through that again, but there's a lot of new stuff, and I know there's some ideas that have been presented, which were presented in those previous SUT seminars and which are now clearly making their way into various of the papers that I've seen over the last couple of days here. So I guess that's all good as well. So let's have a look. Well, the first thing is freefall. Is it a new thing? As I said, there's been no papers about it, but actually, if we go back to the, what's that? Where's the, I'm told this is meant to give me a, no? Oh, where's the light? There should be a pointer.
Yes, it's there, but you can even point there.
Okay, yeah, right, thank you. No? Right, okay. So, well, we know a free falls occurred for a long time. Actually, Barry Lahan just called me and said, oh, well, he saw free falls in Belfast in the 1980s. Well, the first major ones that I know of were at North Rankin A in the 1980s. This site here is on the northwest shelf of Australia, and I guess it was the one really scary freefall. If you look at that profile, you can see here that we've got a CPT profile that goes up and down a bit, and you can see that there was a freefall here. Now, this starts at 60 metres, and actually the pile free fell most of the way to 60 metres, and then it's free falling, and then it had a little bit of a driving, and then it free fell again, and then a bit more driving, free fell again. And basically we ended up at about 112 metres, the pile was still free falling. So this was a bit unusual and unexpected and fairly scary. So it has been a big deal for us in Australia, and we have been dealing with free falls ever since. And a lot of what I'm going to talk about ultimately stems from our works we've done on that. Plus, of course, more recently, we've been having these monopiles. Now, I don't know where this one is. Just appeared on LinkedIn without any reference. So I'd be fascinated if anybody knows where this one is. Of course, we've seen other pile runs as well. This one was presented, I think there was a couple of papers that's mentioned this, the one just a few minutes ago, and also one yesterday, which I've just borrowed these slides from. This was sort of not a free fall in a sense, it was more like a dropped pile, but it was essentially the same mechanisms where a pile was unintentionally released and it went in an awful long way further than people would have expected if they just looked at a standard SRD. So why do piles free fall? So isn't it obvious at the end of the day? Well, if we've got a strong layer overlying a weak layer and the strong soil can't support the pile, the strong soil can support the pile but the weak can't, then we go to free fall. Once we've managed to penetrate through this hard layer here, it will drop from there. And it's, in essence, this is very similar to what you might get with a punch through on a spud can. So it's nothing difficult. It should be reasonably easy to identify, and it should be reasonably easy to address as well. But then we get to the more interesting situations, which is like this. Now, if I were to show you these in the abstract, now there's no axes on these deliberately, they're conceptual sketches, but I've given you here 3 different CPTs, and if I were just to give you those CPTs and said, do any of them look like a free fall will occur? I think you'd probably say, well, no, they all increasing with depth, why will I get a free fall? But I've given you a clue here that this one here, no, this one here, no, but the one in the middle, yeah, maybe. And the one in the middle is because it's a partially drained response. And a partially drained response in a CPT is basically going to mean a transitional soil, which means a silty sand, a sandy silt, or a silt. So if you see those words anywhere in your profiles, they're the sorts of things that should be your first warning to start looking. Now, in the real world, we don't tend to get nice, simple, straight lines, particularly in a transitional soil. It's more likely to be a wiggly blue line like this, going up and down. It will have some low points and some high points. But ultimately, the lower points will be more likely to be the more undrained parts of that profile, and the drain points will be the more drained. And of course, CV can vary dramatically, so quite small variations can lead to quite variable responses. So that's the more likely to be what we'll actually see. But still, there's a net increase with depth, although there's some highs and lows. So let's go through what a traditional thinking of what freefall might mean on this sort of profile. So firstly, if we look at self-weight penetration, well, we would lower the pile, it would reach the point that we see here, and it should stop. Now, that looks pretty a precarious point, I have to say, but that's what it would happen. Now, if you added the hammer weight, which is going to add a lot of extra weight, well, straight away, it would drop through there, so you'd get a very small free fall, and you'd say, well, so be it. Maybe with a bit of dynamics, it might go a bit further, but still, there's a bit of a significant increase, so it should just drop a small distance and then stop again. And if I carried on, just driving the pile as I ordinarily might drive the pile, you might think, well, there'll be a little small drop here, and then it would stop again, and another small drop here, and then it would stop again. And so be it. And then after this point, really, what's the hazard? No, the pile and hammer weight is pretty much always above, well, below, sorry, the resistance that we've got once we've got down to this point here. So thereafter, we should just be able to drive nicely into the ground. The calculated SRD is always higher than our resistance, so it should just be a normal operation. Well, maybe not. So let's think again what could happen. So let's go back to the end of the self-weight penetration phase, and remembering that we are dealing with different resistances for undrained at this end of the spectrum and drained at this end of the spectrum, and then in the middle we've got our partially drained, which is going up and down a bit. So now if we add the hammer weight, what's going to happen? Well, actually, instead of that small drop that I showed you before, that could happen if we get lucky or if we do it slow enough. However, as we add the hammer and the pile starts to move down, we'll get an increase in the pile velocity. And when we get an increase in the pile velocity, if we're in the partially drained space to start with, then increasing the velocity may change the drainage conditions to will change the drainage conditions to a more undrained state. And as we move from a more drained state to a more undrained state, in most cases, that means that the resistance will reduce. And once the resistance reduces, that means there is now even less resistance available to support the pile than we had before. And hence the pile moves faster and the resistance reduces more. And we basically are in a nasty feedback loop, positive feedback loop, where every bit of speeding up of the pile means that the resistance reduces, and ultimately you get a catastrophic situation with the pile dropping uncontrollably. And the pile doesn't just carry on dropping uncontrollably till it's hit one of these little bumps in the profile here. It is dropping uncontrollably until it goes down to intersect with the undrained resistance, and then some, because by that stage it's flying down at a great velocity with a lot of energy, so then it needs extra time to pull up. So it's going to end up penetrating, more likely than not, below, deeper than this undrained SRD, which is potentially very much lower than what you started with, and certainly much lower than a drained SRD. So just in a conceptual space, what does that mean? So we know that we can have graphs with, well, and we've seen this in several presentations today already, VD on CV. Well, we've seen these going back many years now, probably a couple of decades this sort of concept was first explored. And we can treat that in terms of cones, and we can treat it in terms of pile wall thickness. We can also treat it in terms of pile shaft resistance as well. All of these have a sensitivity to drainage. So up here we have our CPT, or pile tip resistance, or even our pile shaft resistance, and as we come along we basically run down this curve. So effectively, if we start in this position, we're going to run down, and we're going to fall down the hill, and the only safe space is when we get to the bottom of the hill. So basically, we're safe against free fall if we're in the undrained space. We're safe against free fall if we're a long way back from the edge of this escarpment, basically, because we're not, even if we speed the pile up during normal operations with hammers and lowering and whatever, we'll stay in a safe space. But if we start off quite close to the edge, then we can drop away. And indeed, this might be one of the most dangerous areas because our CPT might look drained, and in reality, it might be drained, but it may only just be drained. So again, you're looking for the silt content. If there's silt content and you're just about drained, then that might still be dangerous. If you're already well down this chart, well down this slope when you start, well, the drop is smaller. It's still substantial, but it's smaller. So the closer you are to the bottom of here when you start, the better, or being a long way back from this edge. They're the spaces we want to be. And also remember that our relative dimensions do not favor. So here we've got our typical cone of 35 mil, and our wall thickness, which could be anywhere from 25 to 120 mil, if we're just looking at the drainage on the tip. So the cone will drain quicker than the tip of the same diameter. So in most practical cases, the pile tip will have slower drainage than the CPT. So even if our CPT says the situation is drained, then in reality, our pile tip may start off in a more dangerous position. And this can move an apparently safe starting condition to a dangerous condition. Now, I've seen around, written in various, mostly LinkedIn blogs, it has to be, says people talking about liquefaction. I had a discussion with someone a couple of days ago that suggested liquefaction is a part of the mechanism. I really don't think liquefaction plays a significant part in what is happening with pile freefall or pile runs. So let's just revise ourselves what liquefaction means. There's two types of liquefaction. We can have flow liquefaction, which basically occurs when you either have a monotonic response, stress strain curve that goes up and reaches a peak and then drops away very quickly, and can drop away in the most extreme situation to virtually no strength at all. And I don't know if you've ever seen, there's some amazing videos online of flow liquefaction events involving dams failing in Brazil, and there is an extraordinary one of a city almost floating down a hill in Indonesia, which is quite extraordinary. It literally looks like it's going down a river. Well worth checking out if you want to see flow liquefaction. Flow liquefaction can either be triggered statically, or you can trigger it by a few cycles of loading, which bring your strain over and you intersect here and you drop away and then it's all over. So that might sound tempting, but the problem with that is that only occurs in very loose soils. And this sort of loose soil is very rare offshore, since wave action will generally densify soil to at least a medium dense state, not necessarily a very dense state. If you're in the North Sea, it tends to be very dense, but elsewhere, we are definitely seeing more medium dense. And these stills might still be contractive in the undrained space, but they won't exhibit a flow liquefaction where we're losing all of our strength to virtually nothing. But that can be triggered statically, so that could be relevant in such soils if they existed. Then there is the more common type of liquefaction we worry about in offshore, which is cyclic mobility. So this is where we put cycles onto our soil, and we have a loss of soil stiffness over a limited strain range. But ultimately, the soil strength will recover at large strains. So as we can see here, as we're cycling the stress strain curve here, it softens to a zero state, which occurs when the stress path goes through this zero state. But it retains dilated capacity such that when you shear it back up again, you still get a high strength. Now, this mechanism may play a part in triggering a freefall, but it can't really play a part in propagating it, because ultimately, to propagate a freefall, it's a monotonic process. We are free-falling into virgin soil, mostly. So where we can see a triggering part is that if we are driving in a cyclically liquefiable soil, such as carbonates we have in Australia, or indeed Taiwanese silts, which have become infamous, then you can get an increase in pore pressure with each blow. That will reduce the effective stresses at the pile-soil interface, and this will contribute to initial free-fall triggering of the interface degradation. So we can get degradation, gradual degradation. So for example, we may have put a pile in, it may have stopped, we may then get some setup. As we start hammering it, it looks pretty solid, but each blow is actually generating pore pressure, and then we'll get to a point where there has been a reduction in effective stress, enough to trigger the freefall. But if that was all that was going to happen, it wouldn't freefall very far, because it then moves to a static process going into virgin soils. So it won't contribute anything extra once the freefall is initiated, because in that case, the pile is falling monotonically into virgin soil. However, on the other hand, we have soil remolding. Now, soil remolding we know about in terms of clays, and in carbonate soils we have extremely high sensitivities. So very sensitive soils can remold to very low strengths at large strains. And we need to differentiate here remolding, which is a process where we get low strengths at very large strains, whereas flow liquefaction is something that occurs at much smaller strains. So actually they look similar. They're both post-peak strain softening materials, but this is one that requires large strains to propagate it down to very low values, whereas this is essentially an instability that just drops away instantly. So yes, flow liquefaction is very unlikely to be contributing to free falls, but remolding and very high sensitivity soils are definitely contributing. And anywhere where you see liquidity indices close to or greater than 1 should really be a red flag straight away, because a liquidity greater than 1 means that your remolded strength is probably only a couple of kPa or something of that order. So we can conduct full cone tests in fine-grained soils. That's a good test to work out your soil sensitivity in such soils. But then we have the challenge, what about sands? What is even the concept of remolding in sands? We don't necessarily see it in the normal sense of the word. However, when we drop a pile very fast, we get dynamic effects, then indeed we can have essentially remolding. And the best method I know of for assessing that is to conduct CNS types tests on coarse-grained soil, where you do large cyclic degradation, and we can determine, and we'll see an example later of the sorts of things that will come out of that. So there's some basic ideas about the sort of things to look for. Now I'll talk about modeling of freefall. So there's been a few different models. I think basically they're all the same models I've seen in this conference so far, but there's a couple of differences in what we're doing. So in essence, this starts off mostly the same. We've got a crane, and there's essentially a line that hangs the hammer, and there's a bit of stiffness in this wire. So we've got a force on the crane, and we've got a mass of a hammer. Then attached to that, we've got a mass of a pile. Initially, these two objects are in contact with each other, but once the pile starts to freefall, it will separate from the hammer. It doesn't drag the hammer down. And then attached to the pile, we've got external friction. Now, we have a couple of extra things in our model, which is largely because we have some specifically unique challenges in Australian carbonates, which I'll come on to. And that basically is what we include the mass of the plug of soil within the pile here. And we connect that together via a spring and a slider. So this slider here, between the mass of the pile and the mass of the soil plug, is the internal skin friction. And then we have a spring that connects that together to the mass of the plug. So essentially, that force will essentially propagate through up to the limit of this friction. And then below the plug, we then have another spring, and we have a slider, and that slider at the bottom essentially represents the capacity of the plug. Now, why do we need all that? Well, the reason we need all that is because the sort of piles we have, and indeed even the monopiles that people have been using here, do have some restriction of water flow out the top of them. Admittedly, very little with a monopile, but a lot more in an example I'll show you later of an Australian condition. So if we actually, one way of basically preventing freefall or reducing freefall is to put a restricted vent opening in the top of the pile. And under these ways, water will have to flow out of the pile to get this pile to descend. So this sounds great. All we do is we just put a limited vent opening, and the pile will just glide gracefully down, ejecting water through this hole, and that's that. But this pressure here on the top of this plate is also going onto the plug below, and that is what we've got here with these last two components. F-water1 pile is the force pushing up here, and F-water2 is basically the same pressure, equal and opposite, which is pushing down on the plug. So these forces are constrained and controlled by the vent opening. The bigger the opening, more water will go out there, less pressure will be built up. The smaller the opening, less water goes out, more pressure builds up. And if that pressure gets too high, the plug can fail. So instead of actually the pile it will still go down, but the plug goes down with the pile. So we actually have a plug failure and a pile failure. And that has some rather negative influences, as we'll see later. We've used this model in detailed design since about 2013. There's a couple of papers, Prelude and Ichthys, which have been in conference. So I have mentioned freefall previously in a couple of examples, although it's only being a sort of a little back topic. Before that time, I don't know what people were doing, to be honest. For NRB, for example, I think there was some simple counts done, but we didn't do them. So then we can get to the drainage dependent rate stuff that we were talking about before in our model. So we have normalized velocity here, and here we've got a consolidation index. So we've essentially been accounting for this process implicitly since our original model, where we made decisions about are we going to use undrained or drained conditions based on how fast we thought the PAR was going. But we didn't explicitly incorporate this into our model till about, well, it was 2019. We included it for a job we were doing at the time, where we explicitly incorporated this influence. And in very more recent times, really following the Taiwanese situations, we have now also essentially incorporated the same process for shaft friction degradation as well. So this can be, you can derive your relevant consolidation properties here either basically from first principles and lab tests and whatever, or you can use them using an implicit assumption here, where you actually define a drained and undrained resistance and do an interpolation as to your drainage condition based on that. We also incorporate strain rate dependence. Sometimes we've used a log linear model, sometimes we've used the Herschel-Buckley model, and indeed, it does tend to give you about maybe, or the examples I've got, 20% increase for the end bearing, not such a big increase for the shaft friction. Actually, it can even be a decrease for the shaft friction because of the scale that's involved. So let's go to our first example case. So this is a monopile in silty soil. So this is essentially a Taiwanese example. This is not a real soil case. We do not have permission to use people's data, but this is a synthetically created thing that looks like a profile. So no one will recognize these two profiles, but they are things that look like profiles. So there's two here. We've got profile A, which is a bit stronger in the top, and then it's a bit weaker at the bottom, and then profile B, and then profile A, which is weaker at the top, but then much stronger at the bottom. The monopile we're going to look at here is an 8-meter diameter at the top, but it's got a slightly restrictive opening at the top. Sorry, 8 meters over most of the length, and then it transitions down to 6.5 meters at the top over a 12-meter length. 85 meters long. It's in 25 meters of water. In air weight's about 13.4 meganewtons, and then there's a hammer and sleeve weight of about 5 meganewtons in air on top of that. Now, I've also added onto these cone resistances essentially what we've done, which is we've got essentially a backbone drain curve and a backbone undrained curve. So the backbone drain curve is essentially derived from the upper bound of measured CPT data when BQ is about 0. And okay, you might say, well, what's the base? I keep pressing that wrong button. Hold on. Sorry. I need to get better control on the buttons here. Yeah, so down here we can see, no, we haven't got a lot of data, but when you look at a multitude of CPTs, then you can essentially define from that what the drain limit is. And the undrained limit, in this case, ultimately we've got quite a range of lab tests for these sorts of sites, and they all actually tend to be quite similar. And effectively, they boil down to an SU and sigma V that starts from about 0.7 near the surface, but quickly drops to a steady value of about 0.4 deeper down. So that then is derived basically from our measured SUs from simple shear tests using an NKT of 13. So that derives our backbone undrained curve, which also seems to suggest that, in a few spots we're getting close to the undrained limit, and few spots we're close to the drain limit, but most of the profile is in between those. Then we got sleeve friction profiles as well. So these are really defined looking at, these are the peak skin frictions that we use, which is derived on the CPT sleeve friction. So we've sort of drawn an upper bound line to derive the more drained end of the spectrum and the lower bound line to derive the more undrained end of the spectrum. So now we have both a drained and an undrained friction, and then they are applied with a modified Arm-and-Hamry formulation. Looks like this in terms of our degradation behind the tip. And as you can see, it's dropping to some pretty low values. So the question is, what value do we drop to? For that, we are looking at, as I mentioned, sort of CNS type data. So just to show you why maybe Taiwan is a bit different to some other parts of the world, this is typical CNS type results done from an offshore Australian carbonate soil, and you can see that it's normalized here, but it's dropped to a pretty small percentage of the peak. But then if we look at the Taiwanese silt, it's only a little bit better. So actually, when we cycle these things quite profoundly, aggressively, and drop it down, it really drops to very low strengths. And that's the basis of our selection here. This is slightly weird, this thing, where we have about 5 or 10% of the friction as our ultimate residual. So when we put that all together, we see on here, we've got a plot of end bearing versus, this is the SRD now, pile tip end bearing SRD. And then there are different velocities, 0.3 millimeters a second up to 100 millimeters a second. So the 100 millimeters a second is pretty close to the undrained throughout most layers, except a little spike there. And similarly, the 0.3 isn't really getting up to the drain limit in this particular case. And that then translates into actual overall soil resistances, including the skin friction. Here we can see different velocities, and here we can see our starting profile. So we got our pile and upending tool weight there, and then we've got our hammer and pile weight here. So if we just looked at these on their own, you'd say, well, as long as I just follow one of these lines, all should be good because they're all increasing with depth. That's profile A. This is profile B, which does have some reductions with depth, but still in this sort of area here, all is good, apparently, because we just keep following these lines. If we actually run an analysis of with just a very small initial velocity given to these profiles to get them started, then this is what we end up with. So profile A, which was the one which was softer at the top but stronger at the bottom, actually goes faster and reaches almost 15 meters a second, and about 7 seconds later it comes to a halt, whereas profile B goes a bit slower, 10 meters a second per peak, and after 9 seconds it comes to a halt. Interestingly, the embedment depth for both is quite similar. This one is just over 70 meters, this one's 70. And then here, over here for the profile A, which is the one that just goes below 70 meters, we can see the various reaction forces we've got. So the effective pile weight actually reduces as we go down because these piles starting up, a lot of it's above ground, and submerged weight is reducing therefore as more pile becomes below the water level. The total soil resistance is here. It goes up. It's got dynamic spike, which is sort of coming to a halt about here. And there's various little things going on. And then this is the shaft resistance component, and this is the tip resistance component. So as it comes to a halt, the resistance drops. Now, I have to say, I did check this earlier because I realized that actually this drops below 70 meters, and it's probably, we slightly missed that. We actually have a slight reduction in our cone resistance at 70 meters. So it doesn't make a lot of difference, but it does explain why there's a rather sudden drop here. There should be a drop because the pile is coming to a halt, but it's also dropping because there's a lower cone resistance just below 70 meters than you saw on the previous plot. This is how the sleeve friction, the pile friction varies. So with the Arm-and-Hamre model, you can see that we have the friction fatigue coming in, and there is obviously a high value near the tip, but it's very quickly dropping down to very low values at significant degradation. And these low values are well below the undrained sleeve friction because of this degradation, the remolding process that's going on. And then over on this one here, we can see the essentially the same plots as we saw in the previous graph, but these are now plotted versus depth rather than versus time. So static equilibrium point is around 45 meters if we actually were following this curve. But as it turns out, our target penetration in this case was 55, but we've ended up at 70-odd meters, which is 18 meters above the target. So this particular case would have been a bit of a problem, to say the least. So moving to free-fall arresters. Various types of free-fall arrester have been proposed. Most of these are based on what we call in the water break principle, which is, as I said, stopping the water flowing, restricting water flow out of the pile. This is an example type where we had a floating plate. Now, the reason the plate is floating is it actually is free to ride between two brackets. It had neoprene bumpers on it. The reason for that is because if you put something like this in the middle of a pile and try to drive it, the astronomical driving stresses would be impossible to deal with. But by disconnecting the plate and having it free riding, when you hit the pile, the plate basically gets left behind and the pile will go down, and then the plate will just slowly go down and land on the bumpers. And that just keeps going, bang, bang, bang. But it's much more gentle than trying to drive that plate down on the water. Whereas when the pile free falls, it works the other way around. The pile runs away, the brake gets left behind, and then it crashes up against the upper bumper, and then it drags the whole plate down, and it operates as a free fall arrestor. We use these sorts of things in Australia all the time. There are various variations on the theme. But one thing, as far as offshore wind is concerned, is it's not going to be very effective in shallow water, because if most of the pile is above the water. We did run a case with a Taiwanese case, and to be fair, it did pull up a pile that otherwise disappeared, never to be seen again, but they didn't have them, so it was more of an illustrative case. And obviously this does add extra cost and time and whatever, so if you can get away without using it, that's fine. In Australia, we really have no choice, because as you'll see in the next example, we have even more extreme conditions. So there is a potential improvement if you actually could pump water in to actually build the head, a bit like the positive head idea I had in the previous talk before lunch. But that was for something completely different. But pumping in enough water, that's probably going to be rather a slow process, so it may not be very practical either. And also the other problem, as I said, is the arresting effect can be negated if plug failure occurs. So that is where we get to our second example of carbonate soil with free fall arrestor. This one is a 140 metre long pile. It's about 1 meganewton of pile weight submerged, 145 tonnes in air. We've got a pile and free fall arrestor weight of 5.5 meganewtons, 644 tonnes in air. So we're going to drop this pile. It's got a closure at the top, so it's got a CDA vent of 0.32 metres. So a CD is the discharge coefficient, and A vent is the actual area of vent. There's some uncertainty about that number, so that's a hydraulics question. So we tend to lump this together and then ask the hydraulics people to work out what that should be, depending on the particular hydraulic configuration of the free fall arrestor, which may vary. Here we've got our drained and undrained cunettes. In this case, we've got a cemented layer. This is essentially like a normally consolidated carbonate sandy silt. And then deeper down at about this depth, we move into more of a silty sand. And the main difference is not the strength. The main difference down the bottom is the CV jumps from about 1,000 to 2,000 square metres a year to about 100,000 square metres a year. We also have this cemented layer here, which is a thin cemented layer, which is just enough to hold our pile up at this point. And we can see that here. We've got our resistance, submerged pile plus free fall arrestor, submerged plus free fall arrestor and hammer. It's just balanced. But of course, soon as we go bang, 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 it's going to be not very long before that pile is way over the load and off things go. And in this case, this soil here, this is the plug capacity. And the plug capacity is not sufficient. When the water pressure comes on to transfer the load, the plug is completely overloaded. So now what's going on is that the plug is accelerating as well. So we've now got the plug moving down at 3 metres a second and the pile moving down at 4.2 metres a second. The pile will always go faster than the plug because water is always being ejected through the vent, but nevertheless, the plug is dropping. Now what happens here is that the pile drops down and it gets to about, whatever that is, 35 metres, and at that point the plug stops failing. And then we transition back to how the free fall arrestor is meant to work, which is a fairly gentle gliding down at about 1 metre per second until it eventually comes to a halt 110 metres down. So this is the sort of thing, this is a bit like the NRA situation we saw, but a more recent example. So this is quite extreme, and the reason why it is so extreme is because our skin friction, we are estimating, will be around 1 to 2 kPa in these sorts of soils over very, very extensive depths. It literally turns into a yogurt-like material, yogurt-type consistency material when we remold it. We can see here the plug deflection that occurs. So we've had about 10 metres of plug deflection. And this graph here is showing our resistances. So our static plug capacity is the blue line. So it's high here, but then it drops back as soon as we get through the hard layer. We can see that the green is higher because we've got the rate effect adding to it. So there's about a 20% increase. And then you can see the actual plug force, and there's a small difference just because of the dynamics. and eventually the plug force gets lower than the forces of the capacity, and then the plug fails no more, and all is good for the rest of the free fall. So other free fall mitigation measures we might have: self-weight lowering the pile as fast as possible, moves the penetration to the undrained safe zone in silty soils. Now that's the first thing I would be trying. Might be limited by vessel stability and lowering capability, but I was told the other day of a case where this was done and it worked perfectly, so that was very nice to hear that actually. Clump weight tool, push in the pile, only suitable in very weak soils, e.g. some Australian carbonates. It has been done. I'm not sure I'd recommend it. Increase the pile end bearing. This may not be sufficient on its own to eliminate freefall, but can be used to avoid over-penetration. And this is an example of the sort of geometry we've used in structures, putting in cruciforms and trying to line them up with stronger layers to give us a lot more resistance. So essentially try and make the pile plug. Vibro driving or vibro jetting, although only in non-cohesive and uncemented soils, and don't drop the pile, as we saw in that example earlier, which was a case where the vibro piler managed to drop. And another possibility is to try and tie the hammer and pile together with tight slings, although maybe our installation friends might have nightmares, because ultimately you've got to avoid snatch loads overloading the crane and rigging. But that also applies for vibro driving as well, of course, which I think is that pile sliding that was talked about in the previous talk. So yes, tight slings, they have to be pretty tight, because otherwise you will get horrendous snatch loads, but I don't think it's outside the realms of possibility to come up with an arrangement where they could be tied together. So conclusions: pile free fall or pile run, it's not a new thing, and notable examples date back to the 1980s, particularly in carbonate soils. Recent rapid rollout of OWF into previous uncharted areas is indeed, though, revealing some surprises, and particular caution is required whenever you see weak but silty soils. And the papers presented the soil mechanics of freefall with a strong focus on drainage transitions that occur during such an event, and a comprehensive modelling strategy that allows the risks and consequences of freefall to be reliably assessed. And we've also looked at various freefall mitigation measures and some modelling of them, and they've all got pros and cons, and there is no one-size-fits-all. So let's see. So we'll end up on just one more video of a freefall, because we all like videos of freefall because they're fun. And that will be it, I think, after that. So
Thank you, Carl. A real rock star.